Welcome to Teaching Difficult Concepts with Electude. Today's topic, Strategies for Teaching Electric Drive. So today's automotive program. Things were complicated enough before electric vehicles, and teachers today are often strapped for time just covering the conventional automobile. And now we're adding hybrid and electric to the mix, something that is highly technical and often highly abstract. So what are we to do? Can we simply ignore it? I don't think so. Unlike the transition from carburetors to fuel injection, the internal combustion engine is not going away anytime soon. So this is the reality for the next 20 or 25 years. Let's consider teaching engines. If you teach engines or anything mechanical, you've probably done this. You've probably pushed an engine into the classroom. You've removed the cylinder heads. You've put a wrench on the end of the crankshaft. You've spun the crank. Students have watched the pistons go up and down, and you can explain the four-stroke process. In other words, students can learn how something mechanical works through taking it apart. We teach this way all the time, whether it's engines, brakes, suspension, but electric vehicles is totally different. In fact, how would you explain how this works? How would you explain how an inverter works to students? Would you do it the same way? It's interesting to take one apart if you've ever taken the lid off, but once you look deep inside, what do you see? It's a lot of electronics. And so here I have, just for an example, a number of electronics on the screen here. Which one of these is an inverter? Perhaps you're thinking it's this one here in the upper left hand. It's got some recognizable parts. There's some capacitors and a heat sink. No, this here belongs to a washing machine. Maybe this one here. There's got some transistors there, some heat sinks. Maybe this is the electronics from an inverter. No, this is a microwave oven. Over here we have a television set. Here we have a keyboard piano. This picture in the middle, this is an inverter. So as you see, they all share common looking parts, and unlike an internal combustion engine, we're not going to teach this the same way in the classroom as we've done with things in the past. So how are we going to do it? I can recall as a teacher teaching wiring diagrams and maybe even getting some color crayons out and having students trace circuits. I can recall my time as a technician where I would read the circuit description and then study the wiring diagram to figure out how the circuit works and how to diagnose it. So can we apply this strategy to teaching electric drive? Well, here's a part of a wiring diagram for the inverter. As you can see, there's a lot of wires, and it's important to be able to trace the wires, find the connections, to do a pinpoint voltage test. But we're not going to be grabbing the crayons. We're not going to be teaching students how this inverter works by studying wiring diagrams. So that's not something we can do either. Well, what can we do? This might be a little bit of an extreme example, but perhaps we teach electric vehicle along the same time we're teaching the mechanical parts of the automobile. Maybe we don't need a dedicated electric vehicle class. Maybe we just teach electric vehicles throughout the entire training program. And when students are learning about engines, we can also mention to them something about the electric vehicle. So let me ask you this question. What is the task, or what does a cylinder head do? So you might say, well, the cylinder head, it controls the flow of air, intake and exhaust, in and out of the engine. And it does that with valves. Well, what's the inverter do? It controls the flow of electricity in and out of the inverter, and instead of using valves, it uses transistors. So making that little association, I think, will help students learn and identify part. And is there maybe something Electude can offer to make it a lot easier? So at Electude, we offer you interactive, simulation-based animation lessons. And instead of just showing you maybe 5 or 6 lessons, what I'm going to do here is I pulled some of the graphics from about 3 or 4 different lessons in the Electude platform on Electric Drive. And I'm going to demonstrate just using some very simple animation graphics how you might use our content to teach this subject. So let's first take a look at the inverter here. And using our example of relationships between something that the student maybe already understands and learning something new, let's talk about these capacitors for just a moment. So the capacitors on an electric vehicle, I would kind of consider these to be almost like a shock absorber. It absorbs the ripples and the switching of the AC current. Obviously, there's a lot going on inside this inverter with the transistors switching, changing the DC voltage to AC and the AC voltage back to DC. And anytime you switch on a circuit off and on, you're going to get some choppy voltage there. So these capacitors are able to soak up those voltage spikes and provide a nice smooth flow of energy through the inverter. And obviously it's a little bit more technical than that, but for a student that's learning electric vehicle, I would just simply put that these capacitors kind of act like shock absorbers. Then you have the electronics, just like any computer. It's the brain of the inverter. And then we have the IGBTs. These are the very heavy-duty transistors, and they are always grouped in pairs of 2 to handle a little bit more current. So there's 3 windings in the stator, and so we've got 3 sets of these IGBTs connected in parallel to help control the current moving in and out of the inverter to the motor and back to the battery and so forth. And then we have a set of additional IGBTs that act to switch the boost coil. And we're going to talk about what the boost coil does here toward the end of this presentation. And then also, maybe if you do take an inverter apart in the classroom, one of the interesting things to see is just the flow of coolant, the coolant passages in at the bottom of the inverter. The IGBTs sit directly on top of that. Obviously, there's going to be a lot of heat developed when there's current moving through those transistors, and the cooling system here obviously helps draw that heat away. So let's continue through here, and you might recall that wiring diagram that I showed a few minutes ago. Pretty complex, a lot of wires going in and out of that converter. And one of the things that Electude does, which I think is pretty interesting, and you'll probably start to see this a lot more from even manufacturers, is the use of block diagrams. Think of a block diagram as almost like a pictogram. It tells a story with it's a very simple drawing that tells a story. So if we look at the block diagram here for an inverter, what can we learn through this? Well, first we see here would be a DC connection to the high voltage battery, also kind of a DC symbol here. And then that gets converted to a 3-phase voltage, which is shown here as U, V, and W. But what's interesting, and maybe what you might not think about, we have this arrow here that's kind of going through these 3 phases here. And if we relate this symbol to what we see in wiring diagrams, maybe for resistors, if you see a resistor with a arrow going through it like that in a diagonal direction, that's a variable resistor. So if we take that information, what we know about resistors being variable, if it has an arrow going through there, this is a variable AC. So we're taking a DC fixed voltage that's probably in the trunk or under the vehicle, and we're converting that not only to a 3-phase voltage to run the motor, but a variable voltage. and that will depend upon power demand, torque versus speed, but we can make that voltage variable. So this simple diagram here tells a little bit, gives us enough information to at least understand what's going on inside that inverter. Here we got a block diagram that's a little bit more involved. So here, of course, we have our DC battery and our hybrid ECU. Here's our inverter and three-phase electric motor. And first of all, let's just look at these red arrows so we can see that we've got arrows going both directions. So this inverter takes power or electricity from the battery, converts it from DC to AC to run the motor. But we can also take the AC voltage from the motor when we're braking. When we go into regenerative braking, we can take that voltage and charge the battery. So when we got the pedal to the metal, we're taking energy from the battery, converting it from DC, going to AC. And then we put our foot on the brake, we're taking this AC voltage, and we're converting it to DC to charge the battery. So that's why we show the arrows here going in both directions. We've also got some sensor inputs. So we've got, of course, battery state of charge goes to the hybrid ECU. We've got inputs here from the accelerator pedal and the brake pedal. Accelerator pedal makes sense, but you might ask students, why do we need a brake pedal input? Well, that would be for the regenerative braking. So the hybrid ECU needs to know whether we got our foot on the accelerator or the brake pedal to determine which way we're going to cause the energy to flow. Is it from the battery to the motor or from the motor to the battery, depending upon whether we're motivating the vehicle down the road or we're trying to stop the vehicle. So these are block diagrams, and you can learn quite a bit about how the system works through the study of these. So these IGBTs, they are always connected in parallel, and the reason why is that just there's so much current that's flowing through these. One IGBT is not enough, so they're connected in parallel. And if we were to go here to the next phase here, and I've often, early on before I had Electude, I can remember trying to teach this in the classroom and drawing pictures on the board. But this makes it so much easier having access to animations. So here we got a 300 volt battery. Imagine this being one of the stator windings. And if we need electricity to go through that winding in the direction here that I'm showing, we're going to flip certain IGBTs on, and we can make that circuit or make the current flow through the circuit in that direction. If we need it to go the opposite direction, we can simply shift gears here and make it go the opposite way through just the simple switching of these transistors in a pattern. We can make the electricity go either direction. Obviously, if we can also create a short here if we're not careful. So, but through the electronics in the inverter that has control over those IGBTs, we can manipulate and cause the current to flow through that stator winding in whatever direction is needed, based on the polarity of the magnetism, or if we need to switch from being a motor to a generator. If we, you might say, well, I could probably draw that on the board. Yeah, maybe you could. But what about this here? We got a little bit more complicated thing going on here. So here we're seeing the control of the transistors. Here we're seeing the motor. You can see the changing of the direction here through these stator windings to interact here with the changing of the magnetic field. So as the north and south poles move around, we need to obviously change the direction of that electricity going through those stator windings to change the polarity of our magnetic field. If we speed this up here a little bit, we can just kind of watch and see those transistors switching. If you look at this carefully, though, you'll notice that the motor's moving kind of jerkily here. It's kind of got an erratic um, pattern or movement to it, and but a switch is either on or off. But if you've ever driven an electric vehicle, it's a very smooth experience. There's nothing smoother than an electric vehicle under acceleration. So that motor is not moving in this sort of jerky, awkward pattern. We're used to experiencing on electric vehicles more like what you see here. It's a very smooth pattern. But how are we getting that smooth transition, smooth pattern? It's by running an AC voltage through the motor. But how do we create an AC voltage with switches that are either on or off? So this next graphic here, we're going to talk about how the inverter, not only does it just switch the inverter on and off one time per cycle, but it's pulse width modulating this and creating like a digital sine wave. So this blue, this is the control, and the red is the current. And so by just turning the circuit on briefly, you can see that current starts to build. We turn it off a little bit, and then we turn it back on. We can create this an almost digital AC voltage by varying the pulse width. So those transistors are switching on and off extremely fast to give us almost like a digital sine wave. And we can control the speed and the torque by percentage of on time versus frequency. So if we're going down the road at 80 mile per hour on a smooth road under light load, we're going to increase the frequency. When we're pulling away from a stop sign, however, we need lots of power. We're going to have more current flowing, but the frequency is going to be less. So we can kind of balance our power and torque by controlling both the frequency and the percentage of on time. And the computer's doing this all the time based on all its inputs, the torque demands, torque delivered, etc. Now the boost coil, think of this as almost, if we're going to relate to this to something on a conventional automobile, think of this as almost like an electric turbo. How it works, if you think about how an ignition coil works, how we can boost the voltage from, let's say, 12 volts running through the primary winding to over 20 or 30,000 volts in the secondary winding. Most students who've maybe gone through ignition class can understand the relationship between the primary and secondary and how we can induce a voltage and change that voltage. The boost coil is a little bit different, but it's going to use a lot of the same principles. What we have here is instead of a two windings, we have a single winding. And so in this way, it's almost more like if you think about a fuel injector, and when you turn on that injector, the voltage is going to be dropped across the coil. And then when we turn that circuit off, what happens inside this coil? Well, right now, this coil is being energized, and there's a big magnetic field around this coil. When I shut this off, watch the meter here. When I shut this off, you can see that there's a voltage much greater than 12 induced in the winding. Let's look at that again. So here we're dropping 12 volts across the winding, creating a strong magnetic field. When we switch this off, that magnetic field falls across the coil and induces a voltage that's higher based on the number of turns in this winding. So by quickly turning this circuit on and off, we can take 12 volts and make 60 volts. And if I switch this on and off more, rapidly, what we're going to see over time is an average voltage that's much higher than 12. So let's apply that to this knowledge to an electric vehicle circuit. And by rapidly switching that on and off, we can create, for example, take 300 volts from the trunk and make it much higher, 200 volts from the trunk. So if we look at our zero line here, here's 100, 200, 300, 400, 500 volts from just by pulsing that boost coil circuit on and off, on and off. Of course, we got a diode here that direct the current in the right way. We don't want that voltage spike going the wrong way. We've got a capacitor here. If you think about the role of that capacitor is to kind of soak up some this choppiness here to give us a nice smooth flow of energy going to that motor. We got a resistor here, so when we shut this circuit off, this resistor is going to bleed off this capacitor. So, this here is here again another little simple wiring diagram that you, the teacher, can kind of explain to the student. But in a very short amount of time, using the lessons within Electude along with these graphics, I think we can explain this to students in such a way that it makes sense. So we're taking something that's highly technical, highly involved, and trying to break it down into simple circuits and ways of explaining it that are much easier for students to understand. And so here we're going to kind of put it all together. And so we've got 200 volts in the trunk through the this boost coil. We're going to raise that voltage to maybe 500 or 600 volts. And then we're gonna process that voltage. We're going to create a digital sine wave that essentially provides us a smooth AC current here to our motor. And that's kind of the process of it all, from battery to step-up booster, frequency controller to the motor. There's our process, and all our connections inside that inverter. So in just these few minutes, I've been able to take something that's highly complex, break it down using simple graphics to help teach a concept to students that they can understand. And so that's just some of here again, just a glimpse a little bit into the Electude graphics that you're going to find in the lesson. Obviously, I could have just gone through a lesson with you here in this presentation, but that would have been kind of boring. So here again, what I did, I probably pulled graphics from about 3 different lessons and put them in here, and I just kind of talked through that. So students, on the other hand, they would probably go through the entire lesson on the inverter, the electric motor, etc. And then as a teacher, you can kind of come in after that, review their results, pull up graphics like I did here today, and then explain it in yet a different way. And hopefully that makes it a lot simpler for students to understand.